In this lecture, you will learn about principle of moments and moment of inertia. An ideal lever is essentially a light rod pivoted at a point along its length, and this point is called fulcrum. You have seen a seesaw on the children's playground, and that is the typical example of a lever. Two forces F1 and F2 parallel to each other and usually perpendicular to lever as shown act on the lever at distances D1 and D2 respectively from the fulcrum. The lever is a system in mechanical equilibrium. Let R be the reaction of the support at fulcrum. R is directed opposite to the forces F1 and F2. Therefore, for translational equilibrium, R minus F1 minus F2 will be 0. For considering rotational equilibrium, we have to take moments about fulcrum and the sum of moments must be 0. That is D1 F1 minus D2 F2 is 0. Normally, the anti-clockwise moments are taken to be positive and clockwise negative. In the case of the lever force, F1 is usually some weight to be lifted and it is called the load, and its distance from the fulcrum is called the load arm. Force F2 is the effort applied to lift the load and its distance from the fulcrum is the effort arm. Equation 2 can be written as D1 F1 equals to D2 F2, or load arm into load is equals to effort arm into effort. And the ratio F1 by F2 is called mechanical advantage. If the effort arm is larger than the load arm, then the mechanical advantage is greater than 1. And mechanical advantage greater than 1 means that a small effort can be used to lift a large load. Moment of inertia of a rigid body about a given axis of rotation is the sum of the products of masses of various particles and the square of their respective perpendicular distances from the axis of rotation. Mathematically, moment of inertia is denoted by symbol capital I, and that is equals to m1 r1 square plus m2 r2 square and so on. And its SI unit is kilogram meter square. The moment of inertia plays a similar role as mass does in linear motion. However, it depends on shape and size of the body and also on the position and configuration of the axis of rotation. This table gives you the moment of inertia about the particular axis for different bodies. The moment of inertia of a thin circular ring of radius r about an axis perpendicular to the plane at the center is mr square. Similarly, the moment of inertia of a thin circular ring of radius r about its diameter is mr square by 2. A thin rod of length L about an axis perpendicular to the rod at the midpoint, the moment of inertia is ml square by 12. For a circular disk of radius r, its moment of inertia about an axis perpendicular to the disk at its center is mr square by 2. Moment of inertia of a circular disk of radius r about its diameter is mr square by 4. You have to learn these values, and the proof of these is not in your syllabus. As the mass of a body resists a change in its state of linear motion, it is the measure of its inertia in linear motion. Similarly, the moment of inertia about a given axis of rotation resists a change in its rotational motion about that axis and can be regarded as a measure of rotational inertia of the body. Unlike the mass of a body, the moment of inertia is not a fixed value, but it depends on the orientation and position of the axis of rotation with respect to the body as a whole. As a measure of the way in which the mass of a rotating rigid body is distributed with respect to the axis of rotation, we can define a new parameter, the radius of gyration. It is related to the moment of inertia and total mass of the body, and mathematically it is equals to I is equals to mk square, where k has the dimension of length and is the radius of gyration. For its derivation, consider the figure given below shows a rigid body of mass m, and let m be the mass of each of its particle, denoted by different masses m1, m2, m3, mn, but all of these are same, and that is equals to small m, situated at the distances r1, r2, r3, rn from the axis of rotation pq. The moment of inertia will be m1 r1 square plus m2 r2 square and so on up to mn rn square. By taking common m, you will get r1 square plus r2 square plus r3 square plus rn square. Multiply by n and divide by n in the bracket, and m is the mass of one particle and n are the total number of the particles. So m into n will give you the total mass of the body, and that is denoted by capital M. So I is equals to capital M into r1 square plus r2 square plus r3 square plus rn square divided by n. And this term in the bracket is k square. So the value of k will be the root mean square distance, and mathematically it is equals to r1 square plus r2 square and so on up to rn square divided by n under the root. So the radius of gyration of a body about an axis is the distance from the axis of a mass point whose mass is equals to the mass of the whole body and whose moment of inertia is equals to moment of inertia of the body about the axis. For example, for a rod about the perpendicular axis at its midpoint, k square will be equals to L square by 12. So the k will be equals to L upon under root 12. Similarly, by knowing the value of moment of inertia from the table, you can find out the radius of gyration.